Good morning, all of you. My name is Dr. Shivali Verma, and today's our topic is Schrodinger wave equation, which is the in unit second, okay, of engineering, physics, and application subjects. So, what is Schrodinger wave equation? So, as per if we are going for with definition of Schrodinger wave equation, what is Schrodinger wave equation? Schrodinger wave equation is the equation which expresses the wave function psi of matter wave in a different physical condition, and we have dealt with the psi in our last lecture. So what Schrodinger wave equation actually do? So Schrodinger wave equation describe the wave function in a different physical circumstances. Now, or we can say that this equation tell us the behavior of wave function associated with the atomic particle. The equation can be established just like a ordinary plain progressive wave equation, and there are two types of Schrodinger wave equation. One is a time dependent Schrodinger wave equation, and another one is a time independent Schrodinger wave equation. So time dependent Schrodinger wave equation is applied when particle is change its energy with time, and time independent when particles not change its energy with time. Means if particle is not going to change their energy with time, then we apply Schrodinger time independent. One example which I want to give here, for time dependent Schrodinger wave equation. Suppose there is a free electron and it is moving under the some applied electric field, and we are continuously changing the applied energy of the yeah, potential of a applied electrical field. Then electrons energy is continuously changed. In that condition, the wave associated with the particle is described by a wave function psi, and this wave function psi is expressed by the Schrodinger time-dependent wave equation. In a similar way, if a particle is or an electron which is in the rest condition, or we can say that the particle which is inside the atom, so in this condition, particle is revolving in its shell continuously, but by a constant energy, but it is not going to be change its shell or its energy level. So in this condition, particle is moving inside a shell with a constant energy. So uh, the wave associated with such type of a particle is expressed by the time independent wave equation. Okay, so if particle is changing energy continuously, we apply time dependent Schrodinger wave equation, and if particle is revolving in its constant energy area or a constant energy system, then we apply time independent wave equation. Okay, so as I said earlier that we can establish this equation as like a ordinary plane progressive equation. So here is a derivation. So we have started with the classical mechanics plane progressive wave equation. So suppose that there is one wave traveling with the velocity v in a x direction, then according to classical mechanics, the wave equation is given by uh, square by dx square is equal to 1 upon v square d square by dt. This is which is the general wave equation for a particle. Now, if we assume that a matter wave associated with a particle m, mass m, freely moving with a velocity, in this condition, or the in a is analogous to the above wave, so that the wave equation, in this above wave equation, the wave function y is changed by the sun, because now we are taking a particle and it is moving with the velocity v, and now this particle is behaving like a wave. So in this condition their wave function is going to be changed. For the plane progressive wave our wave function is y, but for the matter wave our wave function is psi. So in above equation, we change y by a psi. And this is the velocity of a single wave. And in quantum physics, the velocity of single wave is denoted by Vp. And what is Vp? Basically, it is a phase velocity. And we know that the phase velocity is given by omega by k. So we substitute the value of Vp here. So as it is in a downside, that's why it's written as a omega upon k square. Okay. So now we can take a arbitrary solution of this equation. As we know that psi is a complex nature, that's why its solution must be in a complex way. So as we have taken here a arbitrary solution of this equation, and that solution is psi is equal to a e raised to power I omega minus I omega t minus kx. Now in this solution, we have seen that psi is only shows the wave nature, not a particle nature. But matter wave consists by a particle basically. Whenever the particle is moving, then only the matter waves are generated. Okay. So now we are going to change this wave nature means omega and k are the actually a wave nature. Omega represent the frequency and k represent the propagation constant, and both are the angular here. So how we can convert this? We can change omega or k from wave nature to the particle nature, or we can take a wave nature as well as particle nature in this equation. So as we know that by the Planck's law, E is equal to h nu, and nu we know that it's a linear frequency. So linear frequency is connected with the angular frequency by omega by 2 pi. So at the place of nu, we substitute omega by 2 pi. Now we know that h upon 2 pi is h cut or h bar. So h upon 2 pi, we have written here h cut omega. So what is now omega? Omega is E by h cut means it is come into the energy terms, and basically frequency is come into the energy term. It means that it is nailed about the wave nature only. Now again we are started with the de Broglie hypothesis. We know that de Broglie hypothesis is P by lambda, and lambda is 2 pi by k. So when we are substituting the value of lambda in the terms of k, what we will get? We get P in the this form, hk upon 2 pi. Now again h upon 2 pi become h cut. So my value of P is h cut k, and then we calculated k. So k is P by h cut. So see here, omega is now converted into a energy and k is converted into a momentum. So this is the wave nature basically, but this is the particle nature. So now I am going to substitute the value of omega and k from equation 2 and 3 to equation 1. So my equation become like that. Psi is equal to A e raised to power minus I h cut Et minus Px. So see here now omega t is converted into a Et and Kx is converted into a Px. So Et is basically represent the wave nature and Px represent the particle nature. Now we have to be solve this equation and in the form of classical wave equation only. But we have to, as we see that the classical waves are the second order differential wave equation. So by this solution, we have to be made again a second order differential wave equation. And as we know that the main function of the wave is taking energy from one point to another point. So here also we consider that wave, our matter wave is also going to be a take energy, and that is the total energy, which is in the form of kinetic and potential energy from one point to another point. So in classical mechanics, E is equal to P square by 2m plus V. But now we are changing it in a quantum form by multiplying psi both sides. So this relation help us to uh, establish Schrodinger wave equation. How? Now we are solving it again. Now we differentiate equation number 4 with respect to time to get the second order differential form. So whenever I am going to be differentiated with respect to t, what I will get, as you know that if we are differentiating e to the power ax, what I will get? If I differentiate it with respect to x, I will get a e raised to power ax. So in the similar manner, if I am differentiating this equation, what I am getting? Minus I e h cut a e raised to power minus I h cut e t minus px. And again you see here e raised to power I h cut e t minus px is behaving like a psi. So I replace this factor by the psi. So now my psi del psi by del t is equal to minus I E psi by h cut. Okay. Because here I'm saying I, but it is an imaginary number, so it is a iota. So iota, we got the iota here. Okay. So once I get the iota here, if I am going to calculate the value of E, if I am calculate the value of EH, I'm looking here. So if I am going to calculate the value of E psi from this equation, what I will get? I will get E psi is equal to minus h cut upon I, iota means, multiply by del psi by del t. Okay, got it? But see here, where is the iota? Iota is an imaginary number and it come uh, where? It come in the division wave, but we need it in a multiplication way. So to get it in a multiplication wave, we can rationalize it. Okay, so how do we can rationalize it? By multiplying the iota uh, and dividing by the iota. So whenever we are multiplying by the iota and dividing by the iota, iota and iota, we know that it's a iota square, and we know that the value of iota square is equal to minus of 1. So what we get? We get minus. So here is also minus and iota and multiply by the iota. We will get also minus. So minus cancel out by the minus and we get the positive number. After that, what left? H cut is left. Del square psi by del t is left. And this iota is left. So what is the value I will get? I will get E psi is equal to I h cut del psi by del t, and this is my equation number 6. Now I got the value of E psi for this equation. Now again I need the value of P square psi. So for P square psi, I am again differentiate equation number 4 with respect to x. So when I differentiate equation number 4 with respect to s, a is as it is, differentiating e raised to power minus I h cut et minus px, we will get this same here. And after that, we differentiate this above the term which is in a power. So what I will get, because et is a function of time, so it is going to be eliminated. Only what things are left? I h cut minus px. So minus minus become a plus, and only I h cut px is left. So when I am differentiating I h cut px, what I will get? I will get I p h cut. So after differentiating the psi with respect to x, I will get this. Now again see here, this value a e raised to power I h cut et minus px is again looking like a psi. So I substitute here psi instead of this value. So this is my value for del psi by del x. But I need the value of p square, not p. So again I am differentiating above equation with respect to x. So when again I am differentiating this equation with respect to x, so what I am getting? I am getting del psi by del x square I p h cut as it is a e raised to power minus I h cut et minus px and multiply by I p h cut. Now, see, again, I'm going to explain it. If I'm differentiating this one, and if I'm substituting at the place of psi again this value, so what happened? If I am this value, so this psi and the multiplication by I by ph cut. So when I am differentiating, I will get this value as it is. Okay, this one which I am covered in the box. And after that, again I differentiating the power. So whenever I am differentiating power, et becomes 0, and what thing is left? Minus minus become plus. Again I get I p upon h cut. So in this way, when I am differentiating twice above equation or psi with respect to p, I am getting what? Del square psi by del x square. This become again a psi. P, when we multiply p by p, we will get p square, and h by h is get h cut square. And when iota is multiplied with the iota, I am getting minus. So what is the value of del square psi by del x? This is the value. But I don't need value of this. I need a value of p square psi. So p is, what is the p square psi? Minus h cut square del square by del square psi by del x square. So I have a value of p square psi now and e psi. Okay, so I'm going to substitute the value of e psi and p square psi from equation number 6 and 7 to equation number 5. So when I substitute, like, what is the actual equation number 5 I have written over here. So what is the value of E psi? E psi is I h cut del psi by del t. So I substituted here. And what is the value of p square psi? P square psi is h cut del square, sorry, with minus sign, and del square, h cut del square psi by del x square. So I substituted here. So, and we don't have a value of p psi. So v psi is as it is over here. So now we get this equation, and this equation is known as a Schrodinger time dependent wave equation. Okay, so till here, thank you very much for listening me. May in our next class we can discuss about the time independent Schrodinger wave equation.